So in this video, I'm going to talk about one of the weirdest things in physics, and that's the Einstein-Podolsky-Rosen, or Epr effect. And it's about how, under the right circumstances, nature can make information travel faster than light. Now, people make out EPR to be a very complicated thing, full of mathematical proofs like the Bell inequality and so on. But I'm going to make it extremely simple, so you don't need to know any physics to understand the Einstein-Podolsky-Rosen effect. So let's see how it goes. So we start in 1905, Einstein's theory of relativity, saying that nothing can go faster than light. Everyone believes that, it's been tested. But then, 30 years later, back comes Einstein with Podolsky and Rosen and proposes this amazing little experiment which exposes some sort of faster than light phenomenon in nature. The experiment couldn't be done at the time, but now it has been done many times, and it shows indeed something goes faster than light. So we're going to ask, how does it do that? Real EPR experiments are done with pairs of particles, photons, but we want to make this as understandable as possible, so we're going to talk about it in terms of pairs of people, twins. So what we imagine is there's this pair of twins who claim they have a special faster-than-light telepathic bond. They can share information with each other faster than light. And actually there's not just one pair of twins, there's a whole population of twins who all claim to have this special faster-than-light telepathic ability. Well, obviously this is something that scientists are going to want to see proof of. And the twins say they can prove it. And here's how. Take each pair of twins, separate them, and ask each of them one question. And we'll have it be questions about food with yes or no answers. So you can ask each twin whether he likes avocado, or whether he likes beef, or whether he likes cheese. Well, it's not so obvious what that's going to prove, but the twins say try doing that for each of us, and you'll see what happens. Alright, so let's get going on the experiment. We set up two questioners very far away from each other, and we'll see in a minute why that's so important. Then we send off the twins, one to each questioner. When one of the twins gets to his questioner, she rolls her dice to randomly choose which of the three food questions she's going to ask. Okay, so she rolled a 2, that's avocado. So she asks him if he likes avocado, and he says yes. Meanwhile, far, far away, the other twin has arrived at his questioner, and she's rolled her dice. Now, the important thing here is that when one twin is talking to his questioner, there mustn't be time for a signal traveling at the speed of light to get to the other twin in time to tell him what was being asked or answered at the original location. So, over here, this questioner's rolled a 4, so she asks the twin in front of her if he likes beef, and he says no, and she duly records that. Meanwhile, back at the first twin, the one who asked about avocado, she's recorded that his answer was yes. So there we are. That's the first pair of twins. They've done the experiment, and we can say bye-bye to them. The second pair of twins comes out, and we go through the same process. They split up, one to each questioner. The questioners randomly choose which of the three foods to ask about, and record the answers. And again, the really important thing is that every time we do this, the questioners are so far apart that even if one twin sent a signal traveling at the speed of light to tell his brother what question he'd been asked and what answer he was giving, it still wouldn't have time to get there before his brother gave his answer. So, if they are doing any last-minute coordinating, the only way they could do it would be to use signals that would travel faster than light. And that's the EPR experiment. We do the same thing for the third pair of twins, and then for the fourth pair of twins, and for many, many pairs of twins, because we need to test enough pairs of twins so we can see what recurring patterns there are in their answers. And when we've done a lot of trials like that, we collect all the results together and we start looking for patterns. The question is, can we tell from the data we've gathered whether these twins are sharing information faster than light? Here's a typical sample of the data. A real experiment would use much more than 12 trials,
but 12 is enough so we can see the patterns that emerge. First, let's ask what happens when both questioners happen to ask about the same food. Since the questioners each make a random, independent choice of which of the 3 questions they'll ask, this happens on average a third of the time, so in 4 of the 12 trials we've shown here. Well, what do we see in those cases? A very clear pattern. If both the twins are asked about the same food, then they both always give the same answer. They always agree. This happens consistently when we test hundreds or thousands of twins. This raises the question, how? How are they doing this? The twins say they're using faster-than-light communication. They claim that when one twin is being asked his question and deciding what to say, he coordinates with the other twin to see if he's being asked the same question, and if so, to make sure they give the same answer. And because they're so far apart, this requires a faster-than-light communication channel. Well, okay, that is one possibility, but isn't there a simpler explanation for what we observe? Maybe they're coordinating by pre-planning their answers. Having a plan means that each pair of twins comes up with a pre-programmed set of answers that they agree on in advance. This could be an explicit plan that they agree and remember, or it could just be that both twins have some internal mechanism that's the same in both of them and determines what foods they like. If every pair of twins makes a plan and follows it, then whenever a pair of twins happens to both get asked the same question, they're guaranteed to both give the same answer. So it seems there needn't be any faster-than-light communication going on here. It could just be that every pair of twins generates a plan and then follows it. But no, say the twins, we aren't doing that. We really are using faster-than-light communication. We can prove it. Look at the rest of the data. Well, okay, let's look at it. We want to decide whether the twins could be coordinating the boring way by following a prearranged plan. Instead of focusing on the occasions when both twins got asked about the same food, let's look at the rest of the data. What happens when the 2 questioners happen to ask about different foods? That happens to 2/3 of the pairs of twins, so 8 out of the 12 in our sample. In those cases, how likely is it that both twins will give the same answer? Well, we look down the list, and that only happened twice. 2 out of 8 trials, so a quarter of the time. That's not many times. Actually, it's shockingly few. In fact, this is enough to tell us that the twins are right. They aren't pre-planning their answers. How do we know this? A simple piece of logic called the Bell inequality. So what we want to know at this point is, if each pair of twins was giving their answers based on a prearranged plan, how often would we expect them both to give the same answer when they were asked different questions? The answer is at least a third of the time. That's the Bell inequality. Let's see why this is true. In the EPR experiment, there are 3 possible questions that each twin could be asked. So there's only a limited set of plans they could make. Each plan has to consist of prearranged answers to 3 possible questions. So there are only 4 types of plan. First, there's the 3 yeses plan. They'll say they like all 3 foods. Secondly, there are the 2 yeses and a no plans, where they like 2 of the foods and dislike 1. Then there are the 2 no's and a yes plans, where they only like 1 of the 3 foods. And finally, the 3 no's plan, where they'll say no to all 3 of the possible foods. So now what we want to know is, if a pair of twins has settled on a plan and they're following it, how often will both twins give the same answers when asked different randomly chosen questions? Well, we can just go through the possible plans. For the 3 yeses plan, you can see that no matter which 2 foods they get asked about, they'll always give the same answers. For plans containing 2 yeses and a no, well, since the 2 questioners are choosing their questions at random, a third of the time the questioners will happen to ask about the 2 different foods for which the twins have agreed to say the same thing, yes. And 2/3 of the time they'll be asked about 2 foods for which their plan says to give different answers. So, if they're following this type of plan, then a third of the time both twins will end up giving the same answer. For plans with one yes and two no's, it's the same story. 1/3 of the time, questioners asking two different questions will happen to choose the two that get the same answer. And 2/3 of the time, they'll ask about foods for which the plan says to give different answers. So again, 1/3 of the time, both twins will end up giving the same answer. And finally, for the 3 no's plan, this is like the 3 yeses plan. You can ask about any two different foods, and both twins will always give the same answer. So, no matter what plan a pair of twins decides to follow, when the questioners happen to ask them different randomly chosen questions, the twins should end up both saying the same thing at least 1/3 of the time. There's no possible plan that could lead to them giving the same answer 1/4 of the time. But in the data, that's what we saw. When the two questioners, choosing their questions at random, happened to ask different questions, they got the same answer from both twins only 1/4 of the time. Again, there is no possible plan, no way of prearranging the answers that could lead to that outcome. So we're forced to conclude that, as they claimed, this population of twins is not using the pre-planned answers method to coordinate their responses. Now, let's remind ourselves what's at stake here. We were trying to work out how, when both twins happened to be asked about the same food, they always gave the same answer. One explanation for this was that each pair of twins had built-in or prearranged food preferences, what we called following a plan. But we've just seen that they can't be following a plan, because no plan could give the pattern of answers that we see in the cases when each twin is asked about a different food. The only other possibility is that there's some sort of communication between one twin and the other, something that allows them to coordinate their answers from far away without relying on a prearranged plan. And they're so far apart, and they're asked questions at pretty much the same time, that any sort of communication would have to be faster than light. That's what the experiment tells us. The twins, it seems, were right.
Although I told the story in terms of pairs of twins, this is a real effect that physicists can measure with pairs of photons. Where I talked about asking each twin a randomly chosen question, in the real experiments you put each photon through one of 3 randomly chosen polarization filters, and the yes or no answers correspond to the photon passing through or bouncing off the filter. How do we interpret these experiments? The results for photons show exactly the same pattern that I was talking about with the twins. Their behavior violates the Bell inequality. There is faster than light information transfer between the photons. But that sounds crazy. What about Einstein's theory of relativity and nothing can go faster than light? Is it wrong? Well, you can preserve the theory of relativity if you tighten up the language a bit to say that signals can't go faster than light. A signal is an information sending mechanism that's controllable, so you can use it to send whatever message you like. EPR experiments are consistent with the signals can't go faster than light version of Einstein's speed limit because, as far as we can tell, the faster than light information transfer that we see is not a signal because it's uncontrollable. We can see that the twins, or in real experiments the photons, shared information about their answers, but we can't control what those answers are, so we have no influence over what information is shared faster than light. It's the same with the photons. They somehow tell each other whether they're going to bounce off or pass through the filters, but we have no control over which of those each photon does. As far as we can tell, it's random. So we have a framing of Einstein's theory which makes it compatible with the EPR results, but it's a bit of a mystery. Why are we bringing in the idea of controllability? That relies on ideas like free will that don't normally come into physics theories. They are higher level concepts that ought to emerge when we apply the theory to complex systems like human beings. So Einstein in 1905 was right, there is a speed limit in nature, And Einstein in 1935 adds another insight. There's something subtly mysterious about what exactly that speed limit applies to.